Good morning, everyone. So it's my great pleasure to be here. And so today, as the introduction I'll talk about our team's work for causal decision-making. In particular, I'll talk about how we can tame causality with deep learning. Okay, different from the speaker from yesterday who have many Polish team members, I have another goal. I'm actually missing Polish team members. So in our team, we have Turkish, Swedish, Germans, and I'm here today. I really hope in our team we'll get more Polish team members in the future. Okay, when you think about decision making, right? So what's the key, right? So if I'm thinking about the McKinsey hat. So if I can help the company grow the revenue, I can do, for example, give 20% discount or getting another promotion. What should I choose? So if I know the outcome, if I know what's the revenue, if I do something, the choice will be easy. And think about healthcare. If a medical doctor think about treatment A or treatment B, which one should I give to the patient? So if I know what happens to the patient if I give medicine A or medicine B, the decision is easy. We just choose a better treatment, right? So the key of such decision is really ability to answer the what-if question. What happens if I do something? Not? Great. Okay, so this is hard, actually. Why is hard? Because currently, most of machine learning methods are correlation-based. What happens if I want to think about how can I get good weather? And ice cream consumption is actually a great predictor for good weather. But I think for today's weather, it doesn't matter how much ice cream I eat, the weather will not be good, right? So if you don't think about causality, this mistake will happen. The same for other things. For example, if you just do a predictive method, if I change potentially how much spend I have on the building, your predictor may predict a high revenue. But that's not true. It doesn't matter how much you spend on the building cost, your company will not get high revenue because this is the effect. So current machine learning, deep learning can now be used to answer these questions. What can we do? People goes back to the old, good A/B testing. So we all know how A/B testing is running. We just randomly assign things, like a kind of random assign people into different groups and apply one thing compared to apply another thing. And it's not used everywhere because, of course, it's high cost. Think about healthcare. It's not only high cost, it's high risk. You don't want to randomly assign people new drugs when you don't know what's the outcome. And for finance setting, you also don't want to randomly assign how you deal with your customer because you may harm the customer relationship. With this all high cost, of course, this can only be done at a small scale. Sometimes it happens, but you don't want to do this at large scale. And it takes a long time. Depends on the application. This is a fast changing world. Machine learning papers are called old papers in 6 months. So in many things, after you get the insight from A/B testing, the insight is expired already. And then in the end, A/B testing can tell you whether one thing is useful in general, but it cannot tell you how useful it is for each individual. So it is low resolution. We need personalized decision, and this cannot be done. So wouldn't it be great? Think about how we can get such a table. If at large scale, we can tell you what happens if you do anything. Think about like all different user, for example, companies dealing with, and with all different engagement and action you can do. I can tell you for each of action, how much more revenue you can get. The same for healthcare, for each treatment, for each patient, I can tell you how much health improvement I can provide. The decision is easy. So today, I'm going to talk about causal AI because this is the dream we're working towards. So we would like to be able to provide the answer to the what-if question at scale. And in this way, if we can do that, you can think about it. It's just a machine learning method. And it will be low cost, of course. It will be large scale. It will be real time. We just do a forward pass. And it will be high resolution because, as the table shows, you can answer the what-if question at any arbitrary resolution. Are you all with me? Great. Okay, so I'll dive a little bit deeper into what I mean for all these questions and talk about some work we've done, like our first step, and we'll envision the future as well. So in causality, in causal machine learning, we commonly traditionally have two tasks. One is causal discovery. So for this, it means if we have data, how can we find out the structure, like the causal graph? Is ice cream cause the weather or the weather cause the ice cream? So before we be able to answer this, we need to know which one is the cause, which one is the effect, what's the relationship among everything. So this task is called causal discovery. It is, takes the data, find the graph. And another task is commonly called causal inference. And so for, especially in the narrow sense, so this answers the question, like what happens if I do something? So it's more the second stage. So they want to understand the impact of all different actions. So we call it causal inference. And so commonly, when I actually goes to real world scenario, commonly people have data, historical data, very rarely have experiment data, maybe a subset. I think it's very rarely everything is A/B tested. So you have some historical data, but commonly the goal is the final decision. We want to do the best for the patient, we want to do the best for the customer, we want to do the best for anything we want to decide, right? So we commonly want to achieve this goal. In the end, how do we optimize decision so that we can achieve the best outcome? So to achieve this, as I talk about, this actually need everything. To achieve this, you need the table I talked with you about. So you want to know at high resolution or at arbitrary resolution what happens if I do something. And to know this, you actually require to understanding both the relationship between all these different variables. You need to know which is the cause and which is the effect, and you need to know the functional relationship. How did each action influence the effect you care about? So actually, the goal for such method in many real-world applications is we want to take the data and produce everything for the user. So actually, this is not easy, because if you think about the causal inference, if people know about this field, it commonly acquire additional input. Like there are people like economists, and you need to sit with people, these are the consulting companies, you need to draw the causal graph, like what's the confounders and all this thing, what to control. So this becomes consulting service, where people can gather domain knowledge, they draw this graph, they can complete this task. But in most of the case, this is very limiting because we need many companies, it's very high cost, and it's not a general solution. And as we talk about, why not use a causal discovery? We can just put the data and find the graph. I think that's a good solution, but there are many limitations. So before I talk about the limitation, I'll just give a very brief overview of what are the common causal discovery methods, because I know many people may from like a deep learning and computer vision and other background. I think many years ago when I know this is possible, like including myself, I was completely impressed. I didn't know that was possible before. But so in general, causal discovery have a traditionally three type of method. It is functional causal model, score-based method, and constraint-based method. And think about an example. So functional causal models in general tells you, if I can make some assumptions about the data, I can find the causal graph. So this is a very simple example. If I know the cause and effect are linear, and the noise are additive. So you can think about you have a data looks like this. You don't know x cause y or y cause x. So you know it's a two variable data, two dimension. You want to know whether x, y are causally related and which is the cause, which is the effect. And then with this data, we assume linear model. And then you first try, if x cause y, you do a linear regression. Then you can fit a line like this, and you can plot the x and the residual, the noise, and you can see they're independent. Okay, that's fine. And then let's assume it's y cause x. Let's just test another way. And you do the linear regression again. Then you plot out the y and the residual. So y is assumed cause in this case, and the residual is the noise, additive noise. But you can see they're clearly not independent. So that must be wrong, because the noise should be independent from the cause. So in this way, we can identify it's supposed to be x cause y, and then that's how you find the causal relationship. This is x is cause, y is the effect with assumptions. Okay, so this type of method is very general. There are a lot of research ongoing. You can do it high dimension. You can have, so how to relax the functional form assumption, additive noise model, like a nonlinear model is in general identifiable, but what if the noise and cause have interactions? So the research in this field is very much focused on how can relax all these assumptions to make the solution as general as possible. Another type of causal discovery method is called the score-based method. So this is very simple, idealized. So you get your data. Let's say you have 4 variables, and you want to find the causal graph that you actually can show that the graph that explains the data best with some score method, with some like kind of objective, for example, BIC, will be the best. Will be the actually causal graph. It's actually with infinity data, you can prove this graph is causal. So very simple, you just fit all possible graph to the data and see which gives you the best score. But you can see the limitation of this method. You know, the number of graph grows super exponential with the number of nodes. So after 6 nodes, it's actually almost infeasible to compute anymore. So for this field, traditionally, they have developed many heuristics, how to trim down the search space. And then in recent years, especially after 2018, so it's more, instead of search all these different graphs, can we think about continuous optimization? Because this is discrete optimization. Can we convert it to continuous optimization problem? So it has been great progress in this. And then we'll also utilize this type. And the last type is constraint-based causal discovery. So what does this tell you? So it's like, you assume there is a graph, you want to find the graph. But if you know, like if 2 of the variables are independent or conditionally independent, you can remove the edge. So you can do a search algorithm just to remove the edge one by one, and until there is the skeleton. And after this, there are some basic graph theory. You look at the triplets, for example, A, B, C. If condition on C, A, and B are dependent again, so it must be a collider, so you can orientate this edge. But you can see these are the methods. They care about the graph, and many of them don't even care about how the relationship looks like. The graph they find commonly is not unique. So these are not designed for inference at all. So some of them combined, but there are many problems. So these 2 fields are actually 2 groups of people developed separately for many decades. That's fine. That's many machine learning fields is, right? But they create a problem. Because for the causal discovery, we sometimes output graph. It's a setup graph. I don't know. It's like I can narrow down. One of these 5 graphs is a corrector graph, and they represent it as, they call it complete partial DAG, and also different ancestor graph and other things. But for causal inference, they commonly require a single graph or a single, like a kind of a subset of graph that relates to treatment and effect for their backdoor, like a control variable. So you can see the output and input doesn't match. So putting these 2 fields together is non-trivial. And there is more, like causality needs assumptions. If you don't have assumption, you cannot do causality at all. So for example, like we talked about the functional form assumptions, but you can see, like the method I talked about for the discovery example, that's called the LINGAM, actually. It's linear non-Gaussian additive noise model, so the assumption is linear non-Gaussian. Because if linear Gaussian, it's not identifiable, x, y are the same. And or nonlinear additive noise model, but the function form needs to be nonlinear. And for many inference method, actually the assumption is linear Gaussian. So if you put them together, you solve nothing. You can run it, but you solve nothing. And then there's more problem. So these 2 separate fields, they have been like kind of developed completely separate, but there is arch enemy, machine learning. They never even worked together in the very past years. So these methods, they have beautiful theories, but you read paper, we scale to 6 nodes. These are scalability in many nodes. And meanwhile, machine learning, we care about scalability, real-world impact, but this community will never bring together before. So to really solve it, so our team is actually making a step forward. How can we make deep learning, using deep learning to do deep end-to-end causal inference? We want to do the goal we talked about. Can user just provide us the data? We give you the recommended decision. We do all this output. So this is one of the examples of work. There are many other work in the community, like in different manners, differs in small differences like assumptions, model choices. I'll talk about our work as an example here. Okay, so the key here, so the key contribution is, so if you think about causality, so it's more like the most common language is structural equation model. So you need to respect the structure. So the effect need to be a function of the causes. And then it's always, you can think about the effect is a function of the parents of yourself, the parents are the causes. So you need to respect this structure. And so all this is just the effect generated from causes with a noise, right? So that's the key. You need to think about causes and effect. It's not like using everything else to predict the target. But when you think about it, it is naturally a generative model. So you can think it as just a system, right? So you have extraneous noise, you put some noise, and you respect the structure, and you get the observation. So you can build the bridge between structural equation models and deep generative models. Think about deep generative model, like we can have our favorite normalizing flows, observational autoencoders. If you don't know enough about it, you can hear it from the other room or the recording of the other room. But in this generative model, it tells us you can use external noise to generate your observations. But the thing is, the key here, you just need to generate it with respect to the structure. So you need to generate the data with respect to the causal graph. And so if with this, you can have a large-scale flexible model. You can use deep generative model, this super scalable, it is a graph. We can utilize a lot of things, for example, graph neural network on the implementation, which you heard from Pitar yesterday as well. So it has really great flexibility and scalability. We just need to be respectful to the graph. And that's easy, so I'm part-time Bayesian. So we can think about score-based methods. So we can actually build on the traditional causal theory. So we can actually use score-based methods, think about how to find the graph that maximize how the graph is modeled. And the graph is unknown here. We can utilize other things, for example, variational inference to infer the graph. But if we can learn the graph, the likelihood term, we can use all the tools we have. We can use like normalizing flow with graph neural network, or variational autoencoder with graph neural network. So we have the flexibility here. And in this way, with this objective combined with deep learning, we can learn our graph, and we can also learn the functional relationship together, right? So what's the output of such model will be a distribution of graph, because you learn your graph as unknown variable, and you will have your uncertain estimation. So the output example, toy example, like, this graph may be 0.9, this graph is 0.1, right? So we can infer the graph. Okay, so I just want to show it's actually really essential to consider a theoretical causality. I'm not going to show it, but in general, with a list of assumptions, I'm not getting into the detail here. So we are able to show with such formulation, we can find the true causal graph. So in general, you can see what we did here. So with deep generative models and combined with causal theory, we can get the input and learn the graph because the functional relationships are naturally embedded in the graph neural network. And so we get this down, and then we still get these two steps. This is very easy. How can we do that? We can just use the standard causal theory. So when you do this, so the whole causality, when we want to get to what happens if something, it is a do operation, right? So the do operation is very easy because it just think about if I want to do incentive is $1,000, we just need to cut down the incoming edges. We call it backdoor edges, and then simulate it. So it's a deep generative model. It's extremely good at simulation. And then this intervention distribution is just becoming modulating the graph, cut the edges, and do forward simulation. So this is very scalable, and then we can predict what happens very easily. That just become forward path sampling. And so in summary, so what I presented here is an exemplar method that we can just think about, use input as noise, go through deep generative model. Here you can choose variational encoder, normalized flow, or any other things. And the implementation of the function will be commonly graph neural network. Can think it as just using the graph neural network to learn the functional relationship. So what you get is you can infer the graph. It's actually a distribution of the graph, and you get the functional relationship. With this type of model, you train it once, And all these things become just forward queries. You get the graph, you can kind of arbitrarily can put in different rows, like different users, different companies, and you can think about what happens if you do anything. So all of them are just forward passes. You can easily produce such a big table in real time. And then it can give you all different insights in arbitrary resolution as well. So I can think about in every person, how they respond. I can also think about different group of people. I can also think about in general, how does these different programs respond, right? Okay, so I also want to say this, you can think it as a larger scale general solution because we start with data, we have the whole pipeline. We learn the causal graph, but here we can use our model directly to estimate the treatment effects. But you can also plug in all other traditional causal inference methods like double machine learning and all this. But for the causal graph, you can also combine with other traditional methods. Of course, then you'll have scalability problem, but you can think it as we build the whole pipeline so that we can allow user to start from any arbitrary place and get the decision in the end. Okay, so as a corporate researcher, I can tell you, like in the paper, we got all the state-of-art results for synthetic data and machine learning results. But I want to show you kind of what we're doing in real world, but I cannot show you what exactly the number. So in general, within Microsoft, we tried on our partner data. So Microsoft is a two-business company. We help corporates, so we want to help other companies to grow their own revenue. So we tried on our, we call it partners. We tried our partner program data, and this is a causal graph we discover. So you can think about, for consulting service, if with 5 things, you can draw a causal graph. But with this type of graph, no one can draw. And that's the reason why we need this type of method. And with this graph, we actually can, I remove the axis, but in general, this tells you all different programs and how much growth each of the partner can have. This is an example of a single partner. So this is using the normalizing flow-based approach. And so, of course, I want to say it's not we only care about sales and money. And I want to show you how this graph itself can be used as well. So another project we did, this is using actually a very autoencoder version of the work, is we collaborated with Oxford University Press. So in UK, they print all the textbook. And we also collaborated with one of the biggest kind of digital education platform in UK that's called ED. That's a company, we use their data. What we want to discover the graph of all the topic you can teach in school. And so what we find, so we find this graph, we show it to the education experts, and they find it extremely inspiring. For example, Venn diagram is something they find somehow it's in UK, it's currently taught in year 11. And this is the cause of many other topics that is taught in year 8 or year 9. And then this is completely different order from what is currently taught today. And they realized what happens is in UK, they didn't teach the Venn diagram, but when they have quizzes for other mathematical concepts, they use the Venn diagram already in their quizzes before the student even know what's a Venn diagram. Because of our graph, they actually changed the teaching curriculum, and the Venn diagram is currently put in year 7. So we actually sit with other causal expertise. We find out like many topics that should have been taught earlier, and some of the topics should have been taught later. So we helped the education to really change it and to think about a smart like kind of learning path and a smart curriculum. So this is how a causal graph can help. I also worked with health setting, for example. We also have medical doctors. They look at the graph. Of course, they still need to do the A/B testing, but they use our graph to really think about what is the next A/B testing they want to do. So instead of doing blindly about every single thing, they can think about what they should do so that they can really provide the best treatment to the patient. Okay, so that was actually just an example of work, and we made, in my eye, a really big step towards the world where we can answer what-if questions. We can use machine learning to tell people what to do. So how you can choose your actions that leads towards to better outcome that anyone care about. But this is still an early field. So there are many challenges. In general, I think I put them into 3 categories. So first, machine learning performance in the wild. So causal machine learning is one type machine learning method. We have the method, but you go to the wild, the assumptions are violated, and the performance drop. So if you perform completely wrong, of course the decision will be wrong. So there are a lot of challenges. And then these are about how we can improve the performance and really predict correctly what happens if I do something. Another thing is, the example I gave you is just a simple tabular data. It's a huge table, but it's still tabular data. There are many other different data types. How can every user use our method? Not everyone have a big, nice table. And in the end, causality is different from supervised learning or deep learning models. Evaluation is very hard because you need new experiments to evaluate. How to evaluate and how to deploy it. These are actually a really challenging problem. So we have been continuously making effort in all these different directions, but there is a lot more questions than answers I can provide today. So the first machine learning performance in the wild. So in our team, we have put effort around, for example, you never know what is a true causal relationship. Like we have been assumed like everything you care about is in the data, but that's not true. Like for example, how Google behave may totally impact how the Microsoft revenue goes, right? But Microsoft don't observe how Google behave, right? So these are latent confoundings or the market demand. So these are the factors you don't observe in the data. And if you assume you observe everything, and your method will definitely give you the wrong answer. So we made one step towards this, so we can kind of solve a little latent confounding, but we need to introduce other assumptions, like we call it both ways. So we can make latent confounding in this way, but this variable cannot cause this variable. So be able to handle incomplete information is critical in real-world data, and this is the assumption we are working to relax, but it is very challenging. And then there's a lot of other assumptions we made, because to make the whole machine learning work, we put many different tools. For example, approximate inference. So like when we learn our graph, we use some technique called mean field variational inference. So that actually works if you have a unique graph. But for some time, like the theory tells you, you can never identify the unique graph. It's supposed to be a distribution of the graph. And then with mean field variational inference, it fails because you need to model all the edges dependence and on a large graph. This is a very challenging inference problem because it's discrete space and it's constrained and it's large scale. So we're also trying to further improve the method from an approximate inference point of view, how to improve the accuracy of such method if we can use other different inference methods. But this is the initial step. But in general, these have a lot more open questions on the assumptions, because if we have strict assumptions, it's commonly all violated in real world, the performance will be worse. So you need to think about how to relax all of them, like latent confounding you need from a causality perspective, how to handle latent confounding. This needs the support from causal theory and how to advance this field. And for example, there's other cases. For example, if you have cycles, maybe student learns better when they're encouraged, but then when they're they have some positive quizzes, but then they learn harder, then they get even better score. So these can have cycles. So how to handle all this? So there are a lot of causal assumptions we need to relax so that this type of method can really work in the real world. And then there is also a lot of requirements from the deep learning perspective. We are using a lot of deep learning architecture to tame causality, to make it scalable. But the functional relationship among the causality, so it's very entangled. So what if we don't use like additive noise model? We have other constraints on the function form. How can we mesh the deep learning architecture to the causal assumptions and still make it scalable? And in the end, this is also a field require approximate inference, because when we learn these graphs and all these variables, we need inference method. And all these inference methods have its own limitations. So if people are familiar with like a sampling method, you can have the dependence, but for discrete case, it's very hard to put constraints, and then, or you cannot put gradient information, then it makes the whole method very slow. So just to make such method perform really good in the real world, you need advances for causality, deep learning, approximate inference, and put all of them together to really improve the performance of such type of method. Another thing is, how do you handle different data types? We made some new methods thinking about time series data. So because for the static data, you care about if I do something, what's the effect in the end. But you don't care about the response period. Maybe treatment A, it's in the end doesn't as effective, but it have a very quick response. Maybe treatment B, it doesn't, it takes a very long time to respond, but it can have better performance in the end. So you need to take into account, you want to give more insights, how things change over time, and also many applications, the data is time series. So we actually made autoregressive version in this work. We kind of consider both the lag effects and instantaneous effects, and then we also consider really flexible noise form, but this is a big domain by itself. So there is a data with different sampling frequency and all different things. And then they're missing random, and this all cross selection bias. So all this real world data problem will translate to research questions. And how to advance it is just a very exciting field and to think about it. And moreover, beyond tabular data, our data can be like this. Maybe we want to understand, when the butterfly goes something, the cat catches the butterfly. But the data can be images, it can be audio, it can be natural languages. How do you really put the causal assumption, causal structure for this type of data when what is a variable is not well defined? You need representation learning and concept learning and other things. So handling different data in the real world and think in a causal way, that have a lot of interesting research problems. Okay, so in the end, I want to talk about evaluation and deployment. So in causality, as I said, you cannot just use existing data because the data people may have their own bias. You actually want to evaluate, it can tell you what happens. You need new experiments. And this is very hard, so we actually organize a neurops computation. We collect actually a huge amount of A/B testing data in education domain, so people can look at it and evaluate their method. And meanwhile, causal concept is something not everyone familiar with, how to interpret the causal graph and all these things. So we're also making great effort on building a whole Microsoft causal AI tool with no-code user interface. So in general, for this type of evaluation, this is more a community effort because everyone needs to bring, for example, domain expertise, extra experiments. Otherwise, it's really hard. We don't have an MNIST or we don't have ImageNet for causality yet. And we want to build on each other's work and be able to evaluate and think about when we're good enough to deploy the method is something really challenging. And this is also something fun to work with. So hopefully by now, I convince you this is an important problem, and this is really great time to do the research because causality is a field. It has a long history, and in many real-world applications, people care about causal. People know we cannot only look at correlation. People need to care about causal and think about what to do. But with the theoretical announcement, the impact has been limited. And then on the other hand, machine learning, especially deep learning, we have actually made a lot of algorithm advances. We made a lot of real-world impact, but it has been correlation-based. So both field has matured a lot. This is a really good time. We can think about how to use deep learning to tame causality. In this way, we can guide people what to do. It's go beyond just to recognize between cats and dogs, but really think about what can we do to answer the what-if questions. Okay. So what I have been talking about, I have been saying use deep learning to tame causality. And then I don't know if people have been thinking about the term. Is deep causal learning and causal deep learning the same thing? I think tame, I'll say use the deep learning to help causality is deep causal learning. But then it's also it's deep causal learning, and then there's also causal deep learning. What's the difference? And there's many papers say they're doing causal deep learning, and many papers say it's doing deep causal learning. So in my mind, this actually is the same thing. You can just sit from a different perspective. So think about the model we had. So I have been talking about I need to use this model to answer the question how to find the graph, how to find the functional relationship, to find the treatment effect estimation. But if you can also think about, this is just a deep generative model. It is just a normalizing flow model, and it's just to respect the structure. You can use this model to generate data. You can use this model to simulate data as a regular deep generative model. and it can actually give you many great properties. So for example, deep learning has been struggled with robustness and generalization, right? So you can think about, like I actually have also already worked about it. So if you think about the deep generative model and you try to respect the causal structure, so if you think about all these adversarial attacks, it is just you have observed the image, you have the content, you have its written styles, and you may have this attack. You just manipulate the images, right? So if you can learn all this causal relationship, and then your method will be naturally robust. So we actually shows if just in the image domain, if you have the causal graph, you can build any deep generative model with respect to that causal graph, and you will have amazing robust property. So this is in general like along the axis is how much noise we attack. So these are the different attack strengths, and here is the accuracy. And the green line is the deep generative model if you consider the causal relationship, and the blue one is the one without considering causal relationship. So with this simple model, with this simple application, you can see just the same deep generative model, it can be much more robust. And also, not only robust, you can also think about privacy again. This is a deep generative model, right? So deep generative model, everything people do nowadays, generating data, you can also use the same model if one of them is target. You can also just use it as a prediction model as well. You can use it as a missing data imputation model. So everything deep generative model do, you think about robust, you can also think about privacy. So we actually show if you want to generate like a synthetic data for release, like in healthcare, you don't want to release the raw data, you want to release some synthetic data where the community can contribute without violate the privacy of the patients. So if you just use such a causal model to generate your data, it will be much more robust to membership attack. It will have much more better like privacy property, because think about it, when you think about causal, you remove all the spurious correlations. You don't enter the situation where like all these small identity noise effects and all this are used for your prediction. You respect the true underlying process. And in this way, this will have remove the spurious information and be like kind of generalized better and be able to robust to different attacks. The same, you can think about fairness. So you can define fairness in a way from a counterfactual perspective. So like for example, for a job interview, will that give the same result if I only change the gender? Will that give the same result if I only change, for example, nationality? So this is a way to define fairness, because the fair in a way that for certain protected attribute, the decision shouldn't change, right? So you can think about the fairness from a causal way as well. And if you think about fairness, and the same, like this is a work from, for example, there are many works, this is just an example work, so that using the model, like that is very similar to the model I presented, then you can generate fair synthetic data. You have all different fairness criteria, and then you can think about the data generation should be like a fair among these protected attributes, and using such deep generative model, consider the counterfactual fairness, you can release private and fair data set. And so this is a field, like you can think about causally almost in everything. So I will not say causal is taking over machine learning. So I will say like this is our quote, this recent paper, is causal AI is actually just to provide a principled way to use machine learning. It provides a new way of thinking about machine learning. So think about, like for example, imitation learning. It is, and also offline reinforcement learning. It is using observational data to learn a policy. What's a policy about? A policy is something you want to get to a good outcome, considering your actions. So there are certain equivalents between this offline reinforcement learning and causal decision making. And boil down, if we consider, so the current way without consider causal, it is use a non-causal method to answer the causal question. And if you consider causal in this type of method, there are paper shows, you can be much more example efficient. Your method also have all these nice properties, because all these methods, they are just using a non-causal, like a deep learning architecture to answer a causal question, and all the mistakes are made because of less enough causal considerations. Or you can also think about that just two strong assumptions. And then the same goes to continued learning. Yesterday, you already heard from the first talk. So we need to think about causal consistency. And so how can we continue to learn it? And also the representation learning. What's the disentanglement? Like when I think about if I want to answer causal questions with image data, I need to do the causal representation learning. I need to represent different part of image into a concept, then I can learn the relationship between all different concepts. So representation learning, it may be only the meaningful representation, it's disentangled, it have all this property to really capture, like understand what's going on in the image and videos. So all this as a machine learning field, you can think it in a causal lens. Everything is still valid, and just thinking it in a causal lens, you can formulate in a different way, and you can potentially develop new methods that just brings you better properties and overstep all the difficulties current deep learning methods have. So I think that's the end of the talk because I want to remind you, so we want to do scalable causal AI. This is not only to use deep learning to answer causal questions. So scalable causal AI is you can also think about in a causal way for everything you're doing in machine learning and get inspired. So in the end, just an advertisement, we're hiring for the next year's internship. Thank you.